How does length contraction affect objects at light speed? Imagine traveling so fast that your spaceship shrinks in front of your eyes. Sounds like science fiction, but it's actually a real effect predicted by physics. When objects move very close to the speed of light, strange things happen. One of these is called length contraction. It's a key idea in Einstein's theory of special relativity, which explains how space and time behave at high speeds. Length contraction means that an object appears shorter in the direction it is moving when observed from a stationary point. Think of a spaceship moving past you at nearly the speed of light. To you, the ship looks compressed along its length. This isn't just a visual trick. It's a real change in how measurements are made because of how space itself behaves at high velocities. The faster an object moves, the more it contracts. At speeds much less than the speed of light, this effect is tiny and hardly noticeable. But as the speed approaches the speed of light, the contraction becomes extreme. The math behind this is straightforward but fascinating. The contracted length is calculated by multiplying the original length by the square root of 1 minus the ratio of the speed squared to the speed of light squared. As the speed gets closer to the speed of light, this ratio approaches 1, and the square root approaches 0. That means the object appears almost infinitely short in the direction of motion. But here's the catch. According to the laws of physics, no object with mass can reach the speed of light. As an object accelerates closer to this limit, its energy requirement skyrockets, and it would need infinite energy to actually reach it. So what does this mean for objects at or near the speed of light? They would look drastically compressed from an outside perspective. But for the object itself, nothing changes. The object doesn't feel any different because length contraction is a perspective effect, not an actual physical squeezing. It's like a train moving so fast that from your viewpoint, it looks shorter, but the train itself isn't shrinking. In the context of astronomy and space travel, understanding length contraction helps scientists grasp the limits of how fast objects can travel through space. It also influences how we interpret signals from distant stars and galaxies. When we see objects moving at high speeds, their apparent size and shape can be affected by these relativistic effects. In summary, as objects approach the speed of light, they appear shorter in the direction of motion due to length contraction. This effect becomes more pronounced the faster they go, but it's always a perspective change, not a physical compression. It's a fascinating aspect of how the universe operates at its most extreme speeds, helping us understand the true nature of space and motion at the cosmic level.